Greetings, students of physics. So I'm making this video here to help you out with your Unit 1 homework. Problems 13 through 15 will be topics of the discussion here. So let's start with 13. All right, it says a rock is dropped from a bridge and it hits the water 7.5 seconds later. Your problem may have a different number there, by the way. You always want to start these with a picture. So I don't know, here's my bridge. Presumably, somebody dropped this rock. Now, the rock accelerates down, so the motion diagram for the rock, remember what those are, little, think about a digital camera taking pictures. Click, 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 and superimposing those pictures. These distances would get greater and greater and greater because the rock's speed is increasing. Now, the rock is accelerating down under the acceleration, let me state this better. The rock will accelerate down at what we refer to as the acceleration of gravity, whose numerical value is about 9.8 meter per second. Right, and this is, when you look at your book, this is sometimes called G, acceleration of gravity. And, acceleration is equal to delta V over delta T. Always, always, always true. So use this for the acceleration of the rock, and the delta t is given in the problem, and that will allow you to calculate this, your change in velocity. Now, when you do part A, you'll notice it's got a direction associated with it. So you'll have to select the direction. Now, part B, where it says what is the rock's average velocity. So think about how I'm going to want you to answer this thing. Remember that the rock starts with a velocity of 0. I'm going to call that initial velocity of 0. And it's going to hit with a final velocity that is some number that you're going to calculate. The average is, bigger than this, but less than this. The rock isn't falling at that rate the entire time. You can calculate the average, just like you might think, by averaging these two numbers, the initial velocity plus the final velocity, divide by 2. This is how average velocities, that's how average anything is calculated. If you're given two numbers and you want to calculate the average, that's how you find it. Now, I'm going to put a qualifier on here. In problems like this is only true when your acceleration is constant, and I'll make an entire video about that. But for now, to get your homework done, this is good enough for this problem. All right, part C, where it says what is the height of the bridge. So when you do part C, what we're looking for is a distance here. And the method I like to choose for this, is, let's take our velocity graph, and I'm just going to do this with down positive. So the rock started with a velocity of 0, so at t equals 0, right here it's not moving yet. And then some time later, which in my problem it's 7.5 seconds. Your problem, this number could be different. You're going to have a final velocity, which you calculated earlier. So on the graph, that might be up here somewhere. Again, this is a number that you've calculated earlier, and we're going to make that constant acceleration assumption. And hopefully you've watched my videos on how to find displacements from these graphs. This area here is going to give you and it doesn't matter if we call it a delta x or a delta y or a distance. Any one of these is just fine, really, for this problem. Right? If we call this x, then it would be a delta x. If we call it y, it'd be a delta y. If we just want to say d for distance, that's just fine. This area under this curve will give us how far this thing traveled. That's a triangle. 1/2 base times height. And the base, that's your delta t, and the height, that's the number you calculated before. So that's enough on that one. I think I'll move on here. Okay, number 14. Let's try that one, or chat about it. Okay, it says during takeoff, an airplane goes from 0 to 60 in 6 seconds. So always want to start these with a picture. Just a quick picture is good enough. There's my airplane. Really poor plane, but good enough. The plane accelerates. So again, remember the motion diagrams for that. As time goes on, the delta x's are getting larger and larger. Right, so that is a change in x, right? And that's another change in x, and that's another change in x. And they're getting larger and larger because the plane's going faster and faster. Now part A says to find the acceleration. So I would just start by writing this out. Acceleration is delta v over delta t. There's enough numbers given in the problem to just directly calculate this. And this is given. That should get you the acceleration. That's going to be some number with units of meter over second squared. Part B, how fast is it going after 4 seconds? So I'll just write out the same formula here. And the acceleration, if we assume it's constant, the acceleration number, whatever number you have, is good for the entire time interval. So this right here, given, is a number you would now have. And this is given in part B. And then you're just calculating the delta V. Part C, how far has it traveled by time it reaches the 62 meter per second? So the how fars here start with a velocity graph. Now, I don't want to, do this for you, but say to yourself, what was the velocity at t equals 0, meaning like right here in the picture? Put that point on the graph. Then say to yourself, what is the velocity, the final velocity here? So when we're here, put that point on the graph. And there's the time given in the problem too. And then connect the dots and find the area under the curve. Will tell you the distance traveled. I don't want to do that for you, as again, this is your homework, but that's basically it. Call me or stop in my office if you're having trouble with that. Next, number 15. Let's chat about that. Whoops, that's weird. Try this again. There we go. So let me just do a quick sketch of what we're looking at. There's a graph here. Yeah, super quick sketch. Now, it is a velocity graph. Right, so this is in meter per second. And in real roughly, and again, super rough, it's looking something like this. Then there's some letters down here. It says like A, B, C is right here. All right. Now I think, based on what I'm seeing, I would say that time A, they're talking about this stuff. In time B, they're probably talking about this stuff. Time C, I believe they're talking, oops, do this in a different color here. Time C, I think they're talking about, darn it, one more try on this. Blue. Time C, I think they're talking about this stuff right here. Good enough. All right, so where it says estimate the rise in the run. So for part A, again, they're talking about this part of the curve. So you want this distance is the rise. Actually, let me go back and change that to black. That's the rise, and that's the run. And you're going to read those right off the graph. Part B, so ask yourself, what is the rise from going from here to here? And then the run is this horizontal distance. Part C, this is what they're calling the rise, this is what they're calling the run. But keep in mind that when we compare the red part and the blue part, on the red part we're going right and up. On the blue part it's down and right, and this needs to be taken into account with your numerical answers. Now, for all of these, when they say calculate the acceleration, just, in each case, take your rise over run. So, for example, rise over run. There's your acceleration during that part, and follow suit with the rest of them. So that's enough on that. I'm going to stop that video right there. I hope that this helps get your homework done. Have a great day.